Welcome everyone to another lecture of the practical course Systems Programming. My name is Dennis and I will give today's lecture. The topic of today's lecture is concurrency and synchronization. So in the last lecture, you already saw inter-process parallelism. And today we will look at intra-process parallelism. So last week you saw that different processes run at the same time, each with their own virtual address space. In contrast, today we will look at threads within a single process that all share the same virtual address space. So today we look at threads. So threads divide a program into independent units of computation. For instance, in the example on the right, we consider a video game where we have three different threads, one for the GUI, one for the physics engine, and one for audio. These three threads all share the same virtual address space, which means they can also interact within the same program. However, they all also have their own components. In particular, each thread has its own program counter, thread ID, its own stack, and its own set of registers, which means that it computes largely independently, but it can also communicate with the other threads easily within the same process. Usually, we create threads with the POSIX thread API, where we can create a thread with pthread create, or we can wait for a thread to finish with pthread join. So here we see an example program where the main function creates two threads, and the function running on the thread is here called thread, which is the function on top. So we call pthread create to create these two threads running independently, each with their own ID, ID1 and ID2. And then, crucially, in the main thread, we wait for both of these threads to complete their execution. If we do not do pthread join here, then the main thread may already terminate before waiting for these two created threads to complete. So crucially, these threads, like we said, share the same resources, which includes the virtual address space, which is the heap memory, but it also shares things such as file descriptors and descriptors for other I/O resources. And the crucial thing we need to consider here is that the concurrent access to these resources may affect the domain logic. So we see an example here where we withdraw money from a bank account. And to withdraw money from the bank account, we check whether the current balance is sufficient, and only if this balance is sufficient do we withdraw the amount. So as an example, we can consider two different threads trying to withdraw money at the same time. So if our account only has 50 euros as its balance, which is accessible for both the threads, and both these threads want to withdraw 30 euros, well, that's clearly not possible by our understanding of domain logic, because if you have only 50 euros, you cannot withdraw 60 euros, right? Or withdraw 30 euros twice. So what would happen here, for instance, is if we read the central, the global balance variable, which is 50, and we see that, well, 50 is larger than the 30 we want to withdraw, and then we actually withdraw it by subtracting it from the balance on the left thread. Then on the right thread, we try to do these same steps, namely we read the global balance variable, which is now 20, and then we observe, well, we try to do the check, is 20 larger than 30? Well, it's not, so we do not actually withdraw it. And that makes sense. So only the left thread could withdraw the 30 euros. And as such, this is a sensible interaction, or at least with respect to our understanding of the domain logic of bank accounts. But if we now look at a different interaction between these two threads, we could take a step on the left thread where we we do the first instruction in a function where we take the global balance of 50, and we do the same on the second thread because that one now takes a step. Then on the left thread again, we see 50 is if the current balance is at least the 30 that we want to withdraw, and it is, And on the write thread, we do the same because it has its own local variable b to do this check against. And neither of them has updated the central global balance yet. So then on the left, we succeed. We withdraw the 30 euros. So we set the balance to 20. And on the right thread, we do the same. We also set the balance to 20. And this is an error with respect to our understanding of domain logic, because now both threads have withdrawn the 30 euros from the account and independently updated the balance. But what we here have thus not considered is their concurrent access to this shared resource, which in this case is the account balance. So when you write concurrent programs, you must consider these simultaneous accesses to shared resources to do this correctly. Well, there are various mechanisms to synchronize this between threads. For instance, mutual exclusion, lock-free programming, read-copy updates, or transactional memory, and various others. Today, we will only focus on the first two, which are mutual exclusion and lock-free programming. Let's get started with mutual exclusion. So, mutual exclusion grants a thread exclusive access to a shared resource. So, generally, the terms or a mutex or a lock are somewhat ambiguous and also vary somewhat between communities. For the purpose of this talk, we consider them identical. So a mutex can be held by one thread at a time, and then each thread must acquire the mutex before accessing the shared resource, and then after using the shared resource must release the mutex again. So as an example, we again look at our function to withdraw money from a bank account. And like before, of course, we take the central balance, we check the amount, and then update the balance if there are sufficient funds. However, now, before doing that, we place an acquire mutex function called before this, and after we're done, we release the mutex again. The region of code between the acquire and the release of the mutex is called the critical section. And within a concurrent context, this will be executed atomically, meaning that no two or more threads can access the mutex at the same time, and thus, in this case, cannot access the shared balance variable. So there are various types of mutexes. Well, on the previous slide, you saw a mutex that allows at most one thread to access the shared resource at any given time. Then there are also semaphores, which actually can allow multiple threads to access the shared region at a time, however, still up to a limit. So you can say, hey, at most 5 threads can access the shared resource, but no more than 5. And then there are also read-writer locks. So there can only be one thread writing to the shared resource, or there can be multiple readers. So for instance, if we had another function to check the balance for our shared balance variable, then this is actually fine to have to check the balance by 10 different readers, as long as none of them update it. So there are various ways of implementing locks. There is, for instance, test and set, test and set, MCS, and ticket locks, and various more. Generally, these are implemented with atomic primitives provided by hardware, of which we see an example here. So if you have, or at least given in pseudocode, so here we have a read modify write, it will check whether the current value matches the old expected value, and only if it matches will it update it to the new will it update this shared variable to the new value, and then it will return the current value. And although this is pseudocode, what we assume here is that this entire operation can be performed atomically by the hardware, just as a single instruction. And then this is one mechanism to implement a mutex. So to acquire a mutex, we can keep reading or read modify write, calling this read modify write atomic operation on the mutex, and then look whether it is 0. And if it is 0, we set it to 1. But if it's not 0, we wait until it becomes 0. So it could be another thread has set it to 1 and is still using it. Once it releases it, that other thread sets it to 0. And at that point, our thread observes it's 0, we'll set it to 1, and then the function returns the 0. And that means it would have acquired the lock. So crucially, this read modify write should thus be implemented as an atomic instruction by the hardware. Well, the pthread library offers several different mutexes, which we briefly mentioned before. So there is the mutex, the pthread mutex, where threads enter sleep mode when the lock is busy. So if anyone else is still using the lock, the current thread goes to sleep and will only wake up when the lock becomes available. And that contrasts the spin lock, which will repeatedly keep asking whether the lock is available. So it will ask, hey, is it available? Is it available yet? Is it available yet? Until it becomes available, and it will immediately acquire this. Then there is a pthread read-write lock, which, well, like we said before, allows multiple readers or one writer. So then, of course, you could ask the question, well, what about performance? What if we have multiple bank accounts and we have only a single mutex? Let's say, so there are two bank accounts, A and B, and well, we of course want to guard this critical section, but should withdrawing money from bank account B wait for withdrawing the money from bank account A? Well, in our understanding of domain logic, not. However, in this current implementation, as there is only a single mutex, we do have to wait, and it reduces our parallelism within the program. So these synchronization primitives can hamper the scalability and performance of our program. So this contrasts the coarse-grained against the fine-grained locking mechanisms. So on the previous page, we saw a single global lock that is shared between all the bank accounts. But if we use fine-grained locking, as we see here on the right, where we have a single mutex for each account, that can allow for higher parallelism. Because to withdraw money from account A, you only need the mutex associated with account A. However, this does introduce some additional memory overhead because now we need to keep a mutex for every account. And this can be more challenging to design, especially if you want very fine-grained control. You could have, for instance, a variable or a mutex for every independent variable in your program. But that also becomes a bit excessive because then you have significant memory overhead. Although you do have, of course, much greater parallelism. In addition, this fine-grained locking can cause issues. So, for instance, if we have a function to transfer money from one bank account to another, this function, because it modifies both the bank accounts, it needs to acquire the lock for both these accounts. However, if we transfer money from account A to B by one thread, and then from account B to A in another thread, if this happens simultaneously, we see issues. Because, well, first, by the first thread, the left thread, we acquire the mutex of account A, and the right thread acquires the mutex of account B, because these are the respective from accounts. Then the left thread wants to acquire the mutex of account B, but this one is already acquired by the right thread. And then the right thread actually wants to acquire the mutex of account A, but that is already acquired by the left thread. So now the left thread is waiting for the right thread to complete and release the mutexes, but the right thread is waiting for the left thread to complete and release the mutexes. So now they are indefinitely waiting for each other. This is what we call a deadlock. And there is, in this particular case, there is no way out of this because they will just keep waiting indefinitely. So This highlights another way in which the implementing fine-grained locking algorithms is more challenging, because you can achieve deadlocks where threads cannot make progress at all, as we saw on the previous slide. But we could also have live locks where threads could not make useful progress. Or we could have fairness and starvation issues. For instance, if one thread repeatedly keeps acquiring the same lock, but the other thread never gets the opportunity. Okay, so now we have seen the mutexes, and we move on to lock-free programming. So in contrast to using locks, we can also avoid locks altogether and rely only on the atomic primitives provided by hardware, of which we already saw an example, which was the read, modify, write instruction. The advantage of this is that threads do not have to wait for the lock to become free. So for this example, we consider a linked list with 4 elements, and 2 threads want to simultaneously insert a value into this list. In the previous approach, we could have had a single lock for the entire list, and then the threads would have to wait for this lock to be available before they can insert the elements. However, because these 2 elements, 15 and 35, actually would be inserted in different locations in the list, we expect that this can be done in parallel, right? So this could be the pseudocode of the function that inserts these 2 values in the list. It will first look for the previous value that is lower than the inserted value and its corresponding node, and then inserts the new element before its next element. And then we atomically insert the current elements to this newly inserted element, of which we see the example here, or a visualization, namely, both threads independently insert 15 and 35 before the next element in the list. So crucially, any other thread that still has a reference to this list will still see a valid list with the original 4 elements. Now, the atomic operation, the read, modify, write, will point the current node to the next one, as you see here. And this is an atomic operation, which means also that any other thread that has a reference to the linked list either sees the old version or the new one. You never see a broken, inconsistent representation of the list. It's always either the old or the new one. However, so lock-free programming still has some of the same challenges as fine-grained locking, such as the starvation or the live locks. And it can have some other challenges, for instance, with memory reclamation, as other threads cannot really tell if another thread is still referencing the data or not, because it could have either the old or the new version, and another thread cannot really tell this. Okay, so that concludes our parts with respect to the synchronization between threads. I want to conclude with another issue that can be observed when dealing with concurrent programs, which concerns weak memory. So here we have a program with 2 variables and 2 threads. The 2 shared variables are x and y. And the left thread writes 1 to x and then reads y. And the right thread writes 1 to y and then reads x. Crucially, initially, the variables x and y are 0. Well, so we see an example on the bottom left, where we will first take a step in the first thread, and then another step in the first thread, where we read 0 from y. Then we take a step in the second thread, another step in the second thread, and then we read 1 from x. We end up in a final situation where a is 0 and b is 1. Alternatively, we could have a different interleaving that mirrors this one, where we first take the 2 steps in the right thread, reading 0 from x, and the 2 steps in the left thread, reading 1 from y. And then we end up in the final situation where a is 1 and b is 0. And finally, we could have some interleaving of these, where we first take a step in either of the two threads, updating the values. And then we take the second step in the right thread, where we read 1 from X. And then we do the final step in the left thread, where we read 1 from Y. And we end up in a situation where A and B are both 1. These are, although not all the interleavings, these are all the outcomes that you can observe following this interleaving. However, CPUs actually follow a weaker memory model, meaning that they do not always show the behaviors that can only follow from these interleavings. The reason is that a CPU can have a store buffer, which means instead of writing a value directly to main memory, it will first write it to a CPU or core local store buffer, which will only be written to main memory later, which means that the other CPUs may not directly observe it. So what we could see is the program where both threads will write 1 to their respective variable, but that now consider that these are only written in the CPU local store buffer. Then, when the first thread tries to read Y, it will read it from main memory, because the value written to Y by the other thread is only kept in its in its CPU local store buffer, which means the left thread will actually only observe Y being 0. And the right thread does the same, and will therefore also only observe X being 0. And now you get a behavior that cannot be explained only by the interleaving, namely A and B both being 0 at the end. And this is a consequence of these special hardware behaviors. Or by the way, this is a consequence of how hardware implements concurrency. And these store buffers are very characteristic of the x86 architecture, which you would see in Intel or AMD CPUs. Newer CPUs, such as ARM, or that we more commonly nowadays see, for instance, in the Apple M series CPUs, they actually show even weaker behavior than the original x86 CPUs. However, in our case, if we're implementing programs in C or C++ or in Rust, then the compiler can ensure some of this. However, then you have to implement your program correctly with respect to the memory model of the language. For all our purposes, it would be sufficient to insert full fences, which is a relatively strong primitive, which you would, in this case, place a sequentially consistent fence in between the instructions on both threads. So in between the instruction on the left thread and in between the instruction on the right thread. And that would prevent this behavior, this weak behavior from appearing. There are many more weak memory ordering primitives that you could use. However, they are outside the scope of this lecture. So that brings us to the conclusion. So we have seen that threads allow for lightweight intra-process concurrency. We have seen that synchronization is needed to ensure program correctness with respect to the domain logic. Namely, the thread interleavings can affect the outcome of the program. We have seen that the atomic primitives provided by hardware can allow for implementing efficient synchronization mechanisms, such as a mutex. We have seen that scalable synchronization, such as with fine-grained locking, can be challenging. Then we have seen the other perspective where lock-free algorithms can also be used to implement these algorithms and data structures to further increase performance, as we no longer need to wait for locks. And finally, I have briefly shown how memory ordering can cause issues for your program, and how the related primitives can thus reduce the out-of-order execution that you could observe in practice. Right? That concludes the lecture for today. Thank you for listening.